Okay, in this segment, we're going to talk about a very common, popular graph algorithm called the single source shortest path problem. So the idea is that you have an arbitrary graph. The graph can be weighted or not weighted, or it can be directed or not directed. And we want to find the shortest path. And if it's not weighted, we think of the shortest path as just the fewest hops. But if it's weighted, we have to add up the weight of the different edges between the nodes of the path that we're taking. So of course, there are multiple paths from a source vertex to some specified destination vertex. And the shortest path is the path whose total sum of edge weights is minimum. For example, if we were to look back at the previous graph that I showed an example of, if we wanted to go from Austin to destination Washington, the path Austin, Houston, Atlanta, Washington would add some edge weights to 1560 miles, whereas Austin, Dallas, Denver, Atlanta, Washington, the edge weights would sum to 2980 miles. So of the two paths, this is a shorter path, and if there are no other paths, it's the shortest path. So there are a bunch of famous algorithms to do this, and this is something you would typically study in a basic algorithms class, introductory algorithms class. And of course, in this class, we're more concerned, we have to understand the algorithm, but we're concerned with the implementation of the algorithm, particularly in the C programming language. But this is a very important class of algorithms, and two common ways of doing it are Dijkstra's algorithm and something very similar called the Bellman-Ford algorithm. Note also that breadth first search, I think I pointed this out in the other segment, can be used to solve the problem also in the case that all the weights of the graph are the same, or as I said, it is not a weighted graph, it's a weightless graph. Okay, so in that case, we don't need one of these fancier algorithms. We can just use what we learned already, which is breadth first search, but it's not going to work when we have weights. Okay, so let's look at Dijkstra's algorithm again at a high level algorithmically, and then we'll talk about some implementation issues. So Dijkstra works with either a directed or an undirected graph, and it works with either weighted or unweighted, although we'll typically use it when the graph is weighted. And it's a rare algorithm in that it's what's known as greedy, and that it produces an optimal solution by solving for an optimal solution to a local problem. Okay, so let's do a walkthrough of this algorithm on the simple graph shown to the left, and then talk about how we might implement it, some ways to optimize it, or some implementation considerations. So to carry out the steps of the Dijkstra algorithm, we're going to keep track of some information in this box here, okay? And what we show is in the left-hand column, the label of each node. Then the second column, which we call K, is a Boolean, which determines whether the node is finished being processed or not. So in other words, if the current entry in the table is the final entry, and we no longer have to consider that node, we know we've already found the shortest path, we set K to true. So when we do the pseudocode, we just call the set K of nodes that are complete. This D is the shortest distance from the source node to the given node. Okay, so we're going to set one of these to be the source node, and what each of these rows will show is, or what, I'm sorry, this column will show for each of the rows is the shortest path to that node when we're finished. This is the current value of the shortest path, assuming that we still have processing to do and the node is no longer in the set K. And then we keep track of the parent. So we'd like to know who the parent is so we can trace the path of the path that brings you to the node of the specified distance. Okay, so let's go through it. And if any of that was unclear, it will clarify it when we do the example. So when we start the algorithm, nothing is in the set K, and the distances are all set to infinity for the shortest path, and the parents are all just set to null. Okay, so then we want to start, say, with G. So what we're saying is that we want to find the shortest path from G to, and what I didn't mention is what Dijkstra gives you is the shortest path from G everywhere. So you can either stop when you get to the particular place you're looking for, or you can run the whole algorithm and just take the information that you want from it. Okay, so we say, okay, we're done with G. We're not going to get any better than 0. It has no parent because it's the starting point, and now it's in the set K. Okay, so then what do we do next? We ask, where can we get from G? That's the next step in the algorithm. Okay, from G we can get to D, and we can get to H. So we're going to now add D and H to the table. So D is a distance 2 from A. These are distances from the starting point G. Okay, and the parent is G, and H is a distance 3 from G. I'm sorry, 8, yes, from G, and the parent, it says here, is G. Okay, so those, we don't put false. You could put false here, but I just leave it blank, meaning that their nodes are not complete yet. Okay, so then what do we do next? We go onto this list and we say, what is the next closest place you can get to of the things that are on this list? Okay, so the next shortest distance. So you scan these distances and you find the shortest one. This is actually an opportunity for optimization when you write the code, because you don't want to do a linear search if you have a million or tens of millions of these. So often we implement that with a priority queue. We'll talk about that later. But now in the pseudocode, we just glance at the chart and we say, well, this is the next place you can get. So we're done with it. The next closest place you're always done with. And that's the sense in which the algorithm is very clever. You can knock them off one by solving an optimal local problem. Okay, so we say we're in the set, and you have to think for a second why. You know there can be no, in this, for the first step, it's obvious. You know you can't get to D any better way than going through G. Otherwise, that better way would appear on the list as a shorter distance, but it doesn't appear, right? Nothing else appears. So, you know, it can't be through H because H is already further than D, which is why you're processing D to begin with. Okay, so we're done, but then you have to put in the table all the places you can get from D. And in that case, it's just F, and F is 18 plus 2 is 20 away. Oh, sorry, I missed E. E is 25 plus 2 is 27 away. Okay, so we added 2 more things to our list, but they're not processed yet. And their parents are D now, not G. They're places you can get from D. So let's look on our lists, and the next one we're done with is G. Nothing could be shorter than G. Otherwise, it would appear as the next node we processed on this list potentially. But since all these distances are further, and they're all the places you can get from G and D, then we know that there can't be anything shorter. So we're going to say H is done. And where can we get from H? We can get to B and A. And you have to add 2 H's distance. So H is 3, so this is 12, and this is 7. Okay, so we're going to add 12 and 7 with parent H under the A and B node in the list. Okay, and we just knock them off one by one like this. So we scan the list. It can't be in the set K, and it has to be the lowest one, so it's A. Okay, so A is done then. We consider A processed, and we queue up B, which is A 7 plus 8, 15, and F, which is A 7 plus 10 is 17. So we're going to queue up 15 and 17. Okay. Let's see. What did I mess up? I messed up here, huh? The next one, we added A, let's see. Okay, and we're done with A, right? And when we're done with A, we have to have B and F. Okay, sorry, I forgot to say that B and F are already there. So we only update these distances if they're better than the current distances. I forgot to mention that. So B would be 15 away. So there's nothing to update because we already have a path that's 12 away. So let's leave it alone. And F is 17. Current best path to F is through D is 20. So 17 is better. So we're just going to update that 1. And we're going to say the path through A is actually a shorter path. Okay. Very clever algorithm. Then we scan the list and we say, what's here? 12. B is next. Okay, so we're done with B, and we can get to C from B and E from B. Okay, so we're done with B. And now let's think about this. C, we had no other way to get to, so we automatically put down C as 16. And E would be 22, and we have 27 as our best. So we got 2 new entries. C is 16, and now E is 22, both going through B. So we found 2 new parts to our shortest path by going through there. Okay, then we scan our list and we see that 16 is the shortest, which is C. So we're going to say we're done with C. Okay, and then we're on C. Any places we can get that aren't finished already. That's the importance of coloring them red, i.e. putting them in the set. So there's nowhere, we're done. No place we can get from C that we haven't been already and already found the shortest path. That's the cool thing, that you know that you don't have to check this because it can't possibly be better than the one that we found and retired already. That's the cleverness. Okay, so then F is the next one we process, right? And so we're done with F. And where can we get from F? Well, no place that we haven't found the shortest path already. So then we're going to look at E, and we can get, let's see, a little sneaky. So didn't notice that from F, you can get to E. I just missed that long edge in 2 steps. Okay, so to get to F is 17 steps. So that gives you a 19-step path to E, which is better than the 22-step path. So let's replace that with 19, and then we're done. Okay, so this represents the shortest path from G to all other nodes. Okay, and if you wanted to find the shortest path from each node to each other node, you could just run this n nodes times, and in fact, you could do it easily in parallel. One source per processor, say on a multi-core processor, is one way you could speed that calculation up. Okay, so that's the high-level pseudocode, and we'll talk about some issues related to efficiently programming it shortly.